Here are the objectives for the second section of Chapter 8. We'll spend 2 days on it, and the first day will be done using just the double angle formulas, proving them and using them, and then the second day we will use the half angles and then the equivalent versions for the cosine of 2 theta. All of the formulas that you need are on your note card. You'll eventually need to get these memorized, but to put them in order, the first two double angles are sine 2 theta and cosine 2 theta, and we're going to prove where these formulas come from, so if you ever forget them, you can fall back on the proof. And then tangent 2 theta comes from a formula that you learned earlier in the chapter. After those, we move to what's called the half angle formulas. These are helpful if you need to evaluate something like the sine of 15 degrees. There's 3 of those, sine, cosine, and tangent. And then the last part of the section is taking the cosine double angle formula and rearranging different parts of it to produce different things. Cosine 2 theta, which is cosine squared minus sine squared, can be rearranged to make either the sine squared or the cosine squared disappear. So for example, if I change sine squared into 1 minus cosine squared, I'll have 2 cosine squareds and a minus 1. If I decide to make the cosine squared disappear, I would have 2 sine squareds and a positive 1. Both of those can be solved for either cosine squared or sine squared, and the final 2 formulas for this section are ways of getting cosine squared using the double angle formulas. Alright, so the first 2 examples are actually proving the double angle formulas for sine and cosine, and if you use your addition formulas, these are very quick, straightforward proofs. I'm going to start on the left side and say that sine 2 theta is the same thing as sine theta plus theta. Theta plus theta is 2 theta. Well, this is the addition formula, which breaks down into, treating this as my s and this is my t, sine s cosine t plus cosine s sine t. But instead of s and t's, we have thetas. So sine theta cosine theta plus cosine theta sine theta. Well, these are the exact same things with just the order reversed, so I actually have 2 of these sine theta cosine thetas, and that's what we were trying to prove. Cosine 2 theta is pretty much the same thing. Again, I'm going to start on the left side and change my 2 theta into cosine of theta plus theta. We have cosine addition formulas, which are cosine cosine minus sine sine, and instead of s's and t's, we have theta in both spots, so cosine theta minus sine theta sine theta. Cosine theta times cosine theta is cosine squared theta. Sine theta times sine theta is sine squared theta, and we get exactly what we were trying to prove. So like I said, if you ever forget the double angle formulas, it's not really that difficult to derive them on your own. The next set of examples starts with a given cosine angle, and we need to find sine, which we've done before, and then the double angles for both cosine and sine. So again, if I'm given quadrant information, I'm going to draw a little sketch that tells me 2 pi and 3 pi over 2 puts me in the third quadrant, where my x's are positive and my y's are negative. In order to get sine theta, I need to do one of 2 things. Sine squared plus cosine squared equals 1, or if I draw a real quick right triangle in the third quadrant, and I'm going to use my sketch as an assist. 3 is the x-coordinate, 5 is the hypotenuse. Using some right triangle trig, the y-coordinate is 4. So sine theta is going to be 4/5, and I know that in the fourth quadrant, the sine is negative. So now that I've got sine theta is negative 4/5, I can use the double angle formulas to quickly derive cosine 2 theta and sine 2 theta. Cosine 2 theta is cosine squared theta minus sine squared theta. Cosine squared theta is 3/5 squared. Sine squared theta is negative 4/5 squared. 9/25 minus negative 4 times negative 4 is a positive 16/25, and when I subtract, I get negative 7/25. Well, you might look at that and say that that doesn't make any sense, because if I'm doing cosine, which is the x-coordinate, and if I looked at my diagram, the x-coordinate was positive, but we're finding the cosine of 2 theta. So if your original theta was between 3 pi over 2 and 2 pi, 2 theta is between double both of these numbers up here. So it's going to be between 4 pi and 3 pi. Well, on a diagram, angles that are between 3 pi and 4 pi, once around the circle is 2 pi, 3 pi puts me right here, 4 pi is there. I know that in quadrants 3 and 4, sometimes you do get negative x coordinates. So this actually is an acceptable answer for cosine 2 theta. And then the last example, sine 2 theta, again using the double angle formula, 2 sine theta cosine theta, 2 sine theta is negative 4/5. Cosine theta we were given as 3/5. Multiplying all that together, there's a 25 in the denominator. 2 times 4 times 3, 24, and again the sign is negative. Is it possible to have a negative y coordinate? Yes. In fact, when you take the double angle, we know that the y coordinate has to be negative because 2 theta is between 3 pi and 4 pi, which puts us in quadrant 3 and 4, and the y coordinate is always negative for those. So sine 2 theta is that answer. The last set of examples involves introducing a variable. I have x equals 3 cosine theta, and again theta is in a quadrant. Between pi and pi over 2 puts me in quadrant 2, where my x's are negative and my y's are positive, and I'm supposed to express cosine 2 theta in terms of x. Well, starting with the double angle formula, cosine 2 theta is cosine squared theta minus sine squared theta. And up here I see an expression, and I think I can get cosine theta out of that, but how do I get sine theta? I'm going to do a little bit of work over here to find both cosine and sine theta so I can plug them into this formula. If I divide both sides by 3, I wind up with x over 3 is cosine theta. So that helps. That takes care of the first part. How do I find sine squared theta? Well, same as usual, sine squared plus cosine squared is 1. Sine squared theta, which I don't know, plus cosine squared theta, which I just discovered was x over 3, equals 1. Sine squared theta is 1 minus, squaring those gives me x squared over 9. I can now substitute 1 minus x squared over 9 into the expression over here and come up with my answer. Normally we'd solve for sine theta, but the double angle formula doesn't need sine theta, it needs sine squared theta. So, finishing up, cosine squared, looking at this here, tells me it's x over 3 squared minus sine squared, 1 minus x squared over 9. Simplifying a little bit, x squared over 9 minus a negative x squared over 9 gives me 2 x squared over 9, and then minus 1. So double checking the x squared terms, x squared over 3, x over 3 quantity squared is x squared over 9, minus a negative becomes positive, and I have 2 of those x squareds over 9. So that's the final answer for cosine 2 theta. And then the very last example asks us to find sine 2 theta using this same given information. Well, again, the sine 2 theta formula is 2 sine theta cosine theta. 2, I'd never solve for sine theta, so over here I need to actually take the square root of both sides and say that sine theta equals plus or minus the square root 1 minus x squared over 9. I need to determine whether it's positive or negative, so I'm going to look at my quadrant information. If I'm told that I'm in quadrant 2, sine is the y coordinate, which is positive. So I'm going to say root 1 minus x squared over 9. And then cosine theta is, looking right here, x over 3. So I have 2x over 3 times the square root of 1 minus x squared over 9. Now that's a pretty good answer, but a lot of times the material inside the square root is going to be simplified because I see a 9 here. So I'm going to get a common denominator, add them together, and then square root the denominator. So 2x over 3 stays there. Inside, in order to get a common denominator, I'm going to change the number 1 into 9 over 9, and I wind up with 9 minus x squared over 9. And while the top doesn't square root, the bottom does. So I'll have 2x over 3 times, when the 3 comes out of the denominator, 1/3, and then root 9 minus x squared. And the final answer is 2x over 9 root 9 minus x squared. And so that is sine 2 theta. So that's it. As you use the double angle formulas over and over again, you'll eventually get them memorized, but they're pretty straightforward.